Let's look at quadratic forms. So far, we've been dealing with linear forms. They are of the form ax plus by, or more generally, a1x1 plus a2x2 plus blah, blah, blah. All of the terms have degree 1. With quadratic forms, all of the terms have degree 2. In R2, they are of the form ax squared plus by squared plus cxy. Now you may think, well, cxy, that doesn't have degree 2. But it does, because the degree of x is 1, the degree of the y is 1, and so this is a term of degree 2. In R3, the terms are going to be of the form a1x1 squared plus a2x2 squared plus a3x3 squared plus a4x1x2 plus a5x1x3 plus a6x2x3. Those last three terms are the cross product terms. Quadratic forms have applications in engineering, signal processing, physics, economics, statistics, etc. Quadratic forms can also be expressed in terms of matrices, more precisely symmetric matrices. That's why we're talking about them in a linear algebra course. So let x equal x1, x2. Compute x transpose ax when A is the matrix 5, 0, 0, 2. X transpose is going to be this row vector, this 1 by 2 vector, 1 by 2 matrix, which is a row vector, times 5, 0, 0, 2 times x1, x2. Multiply these first two together, and we get 5x1, 2x2. Multiply that by x1, x2, and we get 5x1 squared plus 2x2 squared. To be honest, usually when we're dealing with quadratic forms and matrices, we just blow off the brackets and we write it like this. And we say that A is the matrix of this quadratic form. How about A equals 5, 7, 7, 2? X transpose AX is going to look like this. Multiply these two together, and we end up with 5x1 plus 7x2, 7x1 plus 2x2 times x1, x2. Multiply it out, and we get this. In other words, we get 5x1 squared plus 14x1, x2 plus 2x2 squared. How about if x equals x1, x2, x3? Let's compute x transpose ax when A is this 3 by 3 matrix. Okay, you know the routine. So x transpose ax is going to be this row vector times this matrix times this column vector. Notice what we get when we multiply these first two together. x1 plus 2x2 plus 3x3, 2x1 plus 4x2 plus 5x3, 3x1 plus 5x2 plus 6x3 times x1, x2, x3. In other words, we're going to get this hairy mess over here, okay? So x1 squared plus, okay, you got a couple of x1, x2s over here. You got 3x1, x3 matched with 3x1, x3, 5x2, x3, 5x2, x3, and you got a 4x2 squared, 6x3 squared, and so this is what we end up with. Note the pattern. The coefficients of x1 squared, x2 squared, and x3 squared go along the diagonal. So there's the coefficient of x1 squared. Here's the coefficient of x2 squared, that's going to be a 4, and the coefficient of x3 squared, that's just going to be a 6. That corresponds to this. The coefficient of x sub I, x sub j is split evenly between the ij entry and the ji entry of A. So in other words, in the end, we end up with say 4x1, x2, that's split between the 2 and the 2. And the 6, x1, x3, that's split between the 3 and the 3. And that's because it's a symmetric matrix. And so you're going to end up with a 2x1, x2 and a 2x1, x2. You're going to have, it's going to be duplicated. And similarly, you've got 10, x2, x3. That corresponds to the 5 here and the 5 here. Now let's do the reverse. Let q of x equal 5x1 squared plus 6x2 squared plus 7x3 squared plus 8x1, x2 plus 9x1, x3 plus 10x2, x3. Express this quadratic form as x transpose ax. Okay, turns out A is going to look like this because we can see that the squared terms have coefficients 5, 6, 7, so we know those are going to be the terms along the diagonal. 8x1, x2, that's going to be split evenly between 4 and 4. Again, x1, x2, so we put 4 in the first row, second column, and the second row, first column. So it's split evenly between those. 9 is going to be split evenly here, so we get 9 halves, 9 halves. 10 is going to be split evenly between 5 and 5 here. And we can check our answer. When you multiply all of this out, if you have the time and patience, you do end up with what we wanted, namely q of x. Let's evaluate q of x when x equals 3, negative 1, 4. Q of x is going to be, well, you just plug in 3, negative 1, 4 into this hairy expression. So x1 equals 3, x2 is negative 1, x3 is 4. Sometimes we just write it this way, q of 3, negative 1, 4. Okay, so again, you plug in 3 for x1, plug in negative 1 for x2, plug in 4 for x3 throughout, and we end up with 207. It's easier to work with quadratic forms if they don't have cross product terms. Wouldn't it have been easier to just get rid of these cross product terms? I think so too. So sometimes we use a change of variable to eliminate the cross product term. A change of variable from x to y, or a substitution, is an equation in the form x equals py. Here x and y are an Rn, and p is an invertible n-by-n matrix. Note that x transpose ax is going to be py transpose a py. Py transpose is the same thing as y transpose p transpose, again times a times p times y. If you break out the stuff that's in the middle, you get y transpose p transpose ap y. Since A is symmetric, there's an orthonormal matrix P such that P transpose AP is a diagonal matrix D, which leads to no cross product terms. That's going to be really nice. Then Y transpose P transpose AP times Y is just Y transpose D times Y. And it's really easy to work with something like this. Again, because since it's a diagonal matrix, since D is going to be a diagonal matrix, there's nothing along the diagonal. So for example, make a change of variable that transforms the quadratic form q of x equals x1 squared minus 8x1 x2 minus 5x2 squared into a quadratic form that has no cross product terms. So first, let's express q of x as A transpose AX. So here's our matrix A. Again, we split up the negative 8 into negative 4, negative 4. Now we need to find P. We've seen how to do that. Let's orthonormally diagonalize A. This is a symmetric matrix, so it's orthonormally diagonalizable. We can express A in the form A equals P dP inverse. P is an orthonormal matrix, D is diagonal. The eigenvalues of this matrix, you can find those with a calculator or with Mathematica or Wolfram Alpha or whatever. The eigenvalues are 3 and negative 7 with corresponding eigenvectors 2, negative 1 and 1, 2. Okay, so this is our matrix of eigenvalues. That's D, 3, 0, 0, negative 7. Now let's find P. A is symmetric. The eigenvectors 2, negative 1 and 1, 2 are from different eigenvalues, namely from 3, negative 7. So because they're from different eigenvalues, they must be orthogonal. Are they orthonormal? No, they're not unit vectors. I mean, this is not a unit vector. This is not a unit vector. So we're going to make them into unit vectors. Okay, so here we have this. Instead of 2, negative 1, we have 2 over root 5, negative 1 over root 5. And instead of 1, 2, we have 1 over root 5, 2 over root 5. Our change of variable is x equals py. So q of x, A transpose AX, we saw before there was x1 squared minus 8x1 x2 minus 5x2 squared. The corresponding quadratic form for y is just going to be 3 y1 squared minus 7 y2 squared. And that's because we've got D is just 3, 0, 0, negative 7. Okay, evaluate q of negative 2, 2 with and without this change of variable. So without the change of variable, again, q of negative 2, 2, we saw the formula for q over here. Here's our formula for q. Without the change of variable, q of 2, negative 2 looks like this. Okay, so you got 2, negative 2 minus 8 times 2 times negative 2 minus 5 times negative 2 squared. That works out to be 16. Method 2, with the change of variable, we've got y equals p inverse. Y is p transpose times x. That's another as p inverse times x, same difference. Again, so this is what p looked like. So p transpose is going to look like this. So you're interchanging these two. So we have 2 over root 5, 1 over root 5, negative 1 over root 5, 2 over root 5, times 2, negative 2. Okay, that's going to be our, and then we're going to use that to figure out what the y-coordinate is. So when you multiply those together, you find that the y-coordinate is 6 over root 5, negative 2 over root 5. So we're not going to plug in 2, negative 2. That's what we plugged in for x. The corresponding y-coordinates, or y-components, are 6 over root 5, negative 2 over root 5. And that's what we plug into this quadratic form. 3y1 squared minus 7y2 squared. Okay, this is what we get. Simplify, and we end up with 16. That was method 2. Is that what we got last time? Oh, yeah, that's what we got last time. Okay, so it was a lot easier to use method 2. We're glad we learned how to change variables, aren't we? Well, not really. This technique is far more useful when the matrix is large. If it's a 2 by 2 matrix, gee, you just wouldn't do it in real life.